Hey guys, here's a video on Unit 5, Section 1, Part A, which is solving systems of linear equations graphically. So to start us off, I did post some graph paper, so I'm going to ask that you graph all of the graphs that I do today for your notes. And on this graph paper, I'm going to ask that you graph these two equations on the same coordinate plane. Okay? Alright, so I'm going to graph first the equation y equals negative x plus 3. Okay, remember, just as a review, right, this is my y-intercept, this is my slope. So without a calculator, I should be able to graph this by plotting the point 3 and then going, since this is a negative 1, down 1 over 1, down 1 over 1. Okay, so I'm going to graph that. Okay, so again, as a review, make sure we use a straight edge to connect these points. Make sure we have arrowheads because we know the equation continues on forever and ever. And also make sure we labeled the line with its proper name. Okay, so I'm going to do the same thing for the second equation. We know we have a y-intercept of positive 1. And we have a slope of positive 1. So that's up 1 over 1. All right. So what do we notice about these two lines? Well, hopefully we notice that they intersect. Right? There is a point where these two lines meet. So what does that mean? Well, that means that this point right here, which is the point x1, comma 2, is a point that makes both equations true. Okay? That means it is a solution to both equations. Okay? So that's a good thing. Okay, when we're solving these systems of equations, we're going to be looking for a point that makes both equations true. So we're going to be identifying the point of intersection. Now this one was relatively easy to figure out because we were able to count the points. Another way to look for points of intersection is by looking at its table. So I actually put these into the calculator for this. This is the equation y equals negative x plus 3, and this is the equation y equals x plus 1. And as you look at the table, one way to figure out our point of intersection is by looking for points that repeat. So what do I mean by that? Well, if we look at all of these x values, we look to see if they have the exact same y values. So this one doesn't. And we continue going down until we find this right here. Okay, when you see an x value that has a repeated y value, you know that you have the point of intersection, which we again said is 1, 2. Okay, now let's say this wasn't a nice clean number. Let's say that was our x value is going to be a fraction. We know that fractions don't appear in the table. Okay, which means that we have to figure out another way to find this point of intersection. Well, lucky for us, we have our calculators. So if you plug these two equations into your calculator and follow the following steps, you should be able to get the point of intersection. Okay, so we put our equation into y1 and y2, which we should all know how to do. We look at the graph. If we see a point of intersection, we can use the second trace or the calc menu to use the functions of the calculator to find the intersection point. So which function are we going to use? Well, we've looked at maximum, we've looked at minimum, we looked at 0. Now we are looking at number 5, which is intersect. So this function will find any points of intersection on a graph, whether they're linear, quadratic, exponential. Anytime two graphs intersect, this can find it for you. So once you press this, it's a little bit easier than the zeros and the max minimum. It's going to ask you first curve, second curve, which is just asking you which two lines you want to find the intersection point of. As long as you only have 2 in your calculator, you can just press enter, enter, and as we did the last time, enter for the guess. Okay, so once you press that, at the bottom of your screen, similar to the way the zeros popped up, you should see x equal 1, y equal 2. Okay, and that's the point of intersection, which you can write as an ordered pair. So I am going to ask that you test that for the question above to make sure you have the correct answer. Okay, so let's take down some definitions. So we're talking about a system of equations. A system of equations is basically any grouping of equations that are working together like a system. Okay, so we need both of them working together to get a common solution. So what is that solution? Well, a solution of a system of equations is the point that makes both equations true when substituted in. Graphically, this is going to be represented as the point of intersection. We write it as an ordered pair. Okay, so we're going to write it as a comma b, x comma y, whatever it may be. And we need to make sure that it lies on both graphs. Okay, because again, it's only a solution to both equations if it falls on both of the graphs. So if we take a look at this picture on the right, okay, what is the solution to this system of equations? Well, it's 1, 3. So how do we check this solution? Well, I gave you both of the equations, right here and right here. We're going to check the solutions the same way we check any other solutions, by plugging it in. Okay, but there's a catch. We need to make sure we plug it into both equations and then it makes both equations true. Okay, so let's do that. Y equals negative x plus 4. We want to test the solution 1, 3. So my y value is 3, my x value is 1. 1 minus 4 is 3. It's a solution to that equation. Let's try the second one. Y equals x plus 2. Y equals 3, x equals 1, 3 is equal to 3. That's a solution, okay? So it's only if it works for both that it is a solution to the system of equations. Okay, so now we're just going to do a couple of examples, of unique examples. So we have this equation right here, solve graphically. The first thing we need to make sure we do is we put the equations in slope-intercept form. So this first equation up here is fine. We don't have to make any changes to it. The second equation down here, we need to put into slope-intercept form. So I'm going to stay color-coded so that we can see what goes with what, but please make sure that when you're graphing on your own paper, that since you have only a pencil, that you label every line and that you make tables for these lines so that you can clearly show all your work. So we have 2y minus 6 is equal to 2x. We want to isolate y equals to put in y equals mx plus b form. So we're going to add the 6 first. 2x plus 6. We're going to divide the 2. And we get y equals 2 divided by 2 is 1x, which I actually don't have to write. And 6 divided by 2 is 3. So we get the line y equals x plus 3. So now, let's graph these. For the red line, we're going to have a y-intercept of positive 3 and the slope of 1. Okay. But if you notice, when you go to graph the second equation, that it's actually the exact same thing. So all the points of this graph are going to coincide with all the points of the first one. So if you remember back to when we were talking about these types of lines, these are called coinciding lines, or coincident lines. They are the exact same lines when you manipulate it. So what's going to happen here is we're going to look for the points of intersection. Well, every point of the first line is a member of the second line. So that means that we have infinitely many, I spelled that wrong, many solutions, because every point on both lines intersect with the other line. Okay, so anytime we have coincident lines or coinciding lines, we have infinitely many solutions. Again, it goes back to the idea of how many points of intersections we have. So let's try one more. Solve graphically. Again, we have the first line is great. Already in slope-intercept form, we need to change the second line. 2x plus 3y equals 9. So 2x plus 3y equals 9. We isolate the y. Uh-oh, sorry. We divide by 3. Y equals negative 2 over 3x plus 3. So let's graph the blue line first. So we have a y-intercept of 1 and a slope of negative 2 over 3. So that's down 2 over 3. Down 2 over 3. 3. Okay, and on the other side, up 2 over 3. Up 2 over 3. Up 2 over 3. And we connect them. And we label y equals negative 2/3 x plus 1. And now for the second line. We have a slope, a y-intercept of positive 3. And we have a slope of down 2 over 3. Down 2 over 3. Down 2. And up 2 over 3. Up 2 over 3. Up 2 over 3. So what do we notice about these two lines? Well, it appears from the graph that they will never touch, right? Because there are no points of intersection. Now, we do have to confirm that, knowing what we know about two lines that never intersect. We know that those are parallel lines. And what we know about parallel lines is they have the same slope and different y-intercepts. So let's see if that is true. Do we have the same slope? Well, they both have the slope negative 2/3. Excellent. Do they have different y-intercepts? 2 and 1 are definitely different. So these are definitely parallel lines. So what do we say our answer is? Well, since we're looking for points of intersection and these two lines will never intersect, we say that we have no solution. Okay, so parallel lines have no solution. Coincident lines or coinciding lines have infinitely many solutions. And for everything else, there's going to be exactly one solution when our lines intersect in one place. So I'm going to ask you to pause the video and attempt this. Okay? See how many solutions you have, look at the slopes, look at the y-intercepts, see what you get. I'm going to actually post the answers so that you can check your work. Okay. Hopefully you see that we have one solution here because they intersect in exactly one place. If we look at our slopes, they are different. So we know that they're not going to be parallel or coincident lines. So we're good. Again, work your best to try and get these tables. Make sure you show all your work. You don't want to lose credit for not showing work.